You ever get that feeling? Like, the more you learn, the more you realize just how much is still out there.
Mm-hmm.
That's me with quantum physics every single time.
Yeah,
But hey, that's why we do these deep dives, right?
absolutely.
Today we're tackling a new paper all about quantum entanglement. And trust me, this isn't just some theoretical head scratcher.
Right.
We're talking about the kind of stuff that could revolutionize everything, from computing to communication.
Yeah, absolutely. It's really exciting stuff.
Luckily, we've got our expert here to break it all down.
I'm excited to be here.
So before we get too far, let's make sure everyone's on the same page.
Okay.
Entanglement, in the simplest terms, what are we talking about here?
So entanglement, huh?
Yeah.
Well, you can imagine like two coins flipped far apart. Normally, the outcome of one doesn't affect the other,
Right.
but entangled coins, they're linked.
Okay.
So if one lands heads, you instantly know the other is tails, and it doesn't matter how far apart they are.
Okay.
And that's the thing that even puzzled Einstein, this spooky action at a distance.
Right. This isn't just a physics party trick. This spooky action is the key to unlocking some really powerful technologies.
Yeah.
We're talking like lightning fast quantum computers, super sensitive sensors for everything from, medical imaging to navigation, even communication networks that are impossible to hack.
Yeah,
That's the dream, at least, right?
that is the dream.
But actually detecting entanglement in the real world, it isn't as easy as just looking at our coins, is it?
No, not quite. It's like having a treasure map.
Okay.
Entanglement is the buried treasure, but we need the right tools to actually find it.
Makes sense.
And that's where the Wigner function comes in. This research uses the Wigner function to help us visualize and confirm entanglement, especially in these advanced systems where more traditional methods struggle.
So this Wigner function, paint me a picture. What is it?
Okay.
And how does it help us actually see entanglement?
So imagine a topographical map,
Okay.
but instead of mountains and valleys, it shows the probabilities of different outcomes for a quantum system.
Okay.
And this map is the Wigner function. It captures kind of the essence of that quantum system, its position, momentum, all in one picture.
Okay, so it's giving us a visual representation of this complex quantum state.
Exactly.
But how's that different from the usual ways scientists try to detect entanglement? I mean, what's so special about this quantum map?
So most methods rely on directly measuring a particle's position and momentum.
Okay.
But for some systems, like the trapped ions used in quantum computing, directly measuring those is really, really difficult.
Okay.
This new research, it provides a workaround, a way to detect entanglement directly from the Wigner function itself.
Interesting.
Yeah, it opens up a whole new world of possibilities.
So it's like we've been trying to listen to a whisper in a hurricane, and this research is giving us noise-canceling headphones.
Exactly. That's a great way to put it.
Perfect.
Yeah.
All right, so we've got our Wigner function, this amazing map of the quantum world. Now, how do we actually use it to pinpoint entanglement? Are we talking like a big flashing X marks the spot kind of thing?
It's a bit more nuanced than that. But the paper does give us 3 powerful criteria to work with. Think of them as specialized tools in our entanglement detection kit, each revealing entanglement in a different way.
Okay, I'm all about having the right tools for the job.
Yeah.
Let's hear about these entanglement detectors.
All right, so criterion number 1, it's all about slicing and dicing.
Okay.
Imagine taking our Wigner function map, and we're going to make cuts through it at all different angles.
Okay, so far so good. We're slicing our quantum map. Now what?
By analyzing the shape of those slices, you know how the probabilities are distributed along those cuts?
Yeah.
We can actually tell if the underlying state is entangled or not.
Wow.
And this method, it's especially powerful for analyzing what we call Gaussian states. Those are kind of like the standard model of simple quantum systems.
Well.
So just by looking at these probability slices, researchers can tell if they've got an entangled state on their hands.
Pretty neat. Okay, what about criterion number 2? What's its specialty?
Criterion 2, this is like grabbing a magnifying glass and zooming in on specific regions of our Wigner function map.
Oh, wow.
We calculate the area under those peaks or sometimes those dips.
Right.
And again, that can help us uncover entanglement.
So criterion 1 is about the shape of the slices, and criterion 2 is about the area under the curves. Man, I'm starting to feel like I'm back in calculus class.
Well, I promise no pop quizzes here.
Okay, good.
But you're right, it is all about analyzing the patterns, in the Wigner function.
Right.
And importantly, the second method, It might require fewer actual measurements in the lab compared to some other techniques,
Oh.
which is a huge win for scientists who are working with these very complex systems.
Yeah, that makes sense. Fewer measurements, less time, less resources spent. And in the world of cutting-edge research, I imagine that's a big deal.
Absolutely.
But I'm guessing no single tool is perfect, right?
You're absolutely right.
What are the limitations of this one?
Yeah, no single method is a magic bullet here. Criterion 2, while very effective for certain types of entangled states, isn't as comprehensive for others.
Okay.
And that's where Criterion 3 comes in, ready to embrace the weird and wonderful world of quantum mechanics.
Oh, I do love it when things get weird.
Yeah.
Lay it on me.
Mm.
What's so special about this third criterion?
All right. So this one hinges on kind of a mind-bending concept: negative probabilities.
Okay.
Now, in our everyday world, probabilities can't be negative.
Well,
The chance of, let's say, flipping a coin and getting heads, it can't be less than zero, right?
exactly. Probabilities are always somewhere between 0 and 100%. That's how I like my odds.
Exactly. But in the quantum realm, things are a little more slippery.
Okay.
The Wigner function can actually dip below zero,
What?
indicating these strange negative probabilities.
Okay.
And here's the kicker. Finding these negative patches on our Wigner function map, it's like finding a smoking gun.
Wow.
It's a surefire sign of entanglement.
Okay, I don't know about you, but the first time I heard about negative probabilities, my brain did a full system reboot. It's like the universe is playing a whole different game down at the quantum level.
It certainly seems that way, but that's what makes this research so compelling. These criteria, especially that third one, give us this new way to explore and verify those uniquely quantum phenomena like entanglement.
So we've got these three criteria, each a different lens for spotting entanglement. And it sounds like they're passing the test so far. But let's bring it home. Why does all of this matter?
Well, what's fascinating is that this paper isn't just refining our ability to detect entanglement, it's expanding the possibilities for exploring it in entirely new ways.
Okay.
We've been so focused on those direct measurements,
Right.
and now we have this whole new set of tools based on the Wigner function.
Okay.
It's like we've been trying to conduct an orchestra with only a tuning fork, and now we've got a whole array of instruments to work with.
Okay. I'm getting a sense of, though, why it matters for the quantum physics folks, but
Mhm.
let's be real. Most people listening aren't about to start measuring Wigner functions anytime soon.
Right.
So what's the takeaway for the rest of us? Why should we care about a more efficient way to detect entanglement?
Because it's not just about the detection itself, it's about what this detection enables. Those technologies we talked about earlier, quantum computers that could, revolutionize drug discovery,
Right.
ultra-precise sensors for everything from self-driving cars to earthquake prediction,
Wow.
unhackable communication networks that make our data safer. These all rely on entanglement.
Okay.
This research brings us one step closer to making those technologies a reality.
So it's like saying, why should we care about a better telescope? Well, because that better telescope might let us see further into the universe and unlock secrets about, our place in the cosmos. This research is doing that for the quantum world, and the implications could be just as profound.
That's a great analogy, and what I find most intriguing is how this research pushes us to ask even bigger questions.
Okay.
We've talked about the Wigner function as map, with its peaks, valleys, and those mind-bending negative regions. But what if we're only seeing a fraction of what this map holds?
You're blowing my mind here.
Here.
What else could be hidden within this quantum map? What other secrets of the quantum world are waiting to be discovered?
That's the beauty of science, right?
Yeah.
Every answer leads to more questions. As we continue to refine our tools, our techniques, who knows what incredible new insights we'll uncover about, the nature of reality itself. It's an incredibly exciting time to be exploring the quantum realm.
Absolutely. And on that note of endless possibility, it's time to wrap up our deep dive into the world of entanglement and the Wigner function. If your brain feels a little bit bendy right now, that just means you're catching on to the wonderfully weird world of quantum physics.
And remember, this is just the beginning. The more we learn about entanglement, the closer we get to unlocking its true potential. It's a journey that promises to be full of surprises.
Absolutely. Until next time, keep asking those big questions and never stop exploring the wonders of the universe, big and small.